Hey, this is Brooks Bucklew, and this is my Physics 2212 Lab 4, Faraday's Law. So to introduce, the purpose of this lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil, to model the magnet and tube interaction computationally, and compare our computational predictions with our observed data. Physics principles involved in this lab include the magnetic flux, which is the measurement of the total magnetic field which passes through a given area, Faraday's law, which can be seen above, states that the magnitude of the EMF induced in a circuit is proportional to the rate of change with time of the magnetic flux that cuts across the circuit, and Lenz's law, which can be seen above as well, states that the induced electromotive force with different polarities induces a current whose magnetic field opposes the change in magnetic flux through the loop. Now, physics modeled the falling magnet, and as it falls, it creates a changing magnetic field at each ring. A cylinder is essentially an infinite stack of rings where d flux dt points in a downward direction. According to Lenz's law, the magnetic field due to induced current points upward, and the current flows in a counterclockwise direction from an above point of view due to the right-hand rule. Magnetic force was found using the following formula, where magnetic field was found using the Biot-Savart law. Now, as for our equipment, the procedure of this lab starts with recording physical properties of an aluminum foil cylinder. You need to mark the north pole of the bar magnet, then proceed to hold the tube vertically and drop the magnet north side first from the top opening. Measure the time it takes to reach the bottom and average this time over 5 trials. Our results included an experiment. Experimentally, it was 1.25 seconds, and computationally, it was only 0.33 seconds. Now, our measured and known properties. The aluminum foil tube had a length of 0.3 meters, a width of 0.005 meters, inner radius of 0.025 meters, an outer radius of 0.03 meters. Its resistivity was 2.65 times 10 to the negative 8th ohm meters, and our magnet had a mass of 0.023 kilograms with a magnetic dipole moment mu of 2.1 amps meters squared, which we found from lab 3. Now, observations. So, checkpoint, what happens to the magnet, and how does this compare to a magnet falling in free space? So, a magnet falls in aluminum tube falls a little bit slower than in free space. It has a downward force of less magnitude because the aluminum cylinder applies an upward force on the magnet. And as you can see, our 5 trials with an average recorded time of 1.25 seconds. So, our computational model. First, we created the tube of aluminum foil as a series of rings stacked along the y-axis, where the y-axis is perpendicular to the plane of each ring and passes through the center of each ring. So for our tube, we have a bunch of different rings, which each have a position, a current, a flux, a radius, and an R, resistivity. And then we create the bar magnet, which has a mass and a magnetic dipole moment, which again we found from lab 3. So calculations, again from lab 3, we use the Biot-Savart law, and then we also calculate d flux dt through each ring due to the falling magnet, as seen in the following function. Our following magnet simulation starts with checking to see if the magnet is in a tube. Then we iterate across rings to find the net magnetic force on the magnet. Third, we find the magnet's acceleration. And then fourth, we update the magnet's position accordingly. And finally, we plot the magnet's position and velocity versus time. So here we have a visualization produced by the computation and a plot. As you can see, the magnet falls through the tube, where the force of the magnet goes upwards, but the force of gravity is going downwards, with the force of gravity a little bit stronger. And as you can see in the plot, the velocity is always a negative value, so it's always moving downwards. And the position also is always moving downwards. As you can see at the very end, the velocity speeds up. That's because the magnet exits the tube a little bit, and the tube has less of a force upwards on it, and so it moves a little bit faster. So, in reflection, we ask the question, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The current and resistance are inversely proportional, so the magnitude of the current would grow, the magnitude of magnetic force would increase, and the magnet would fall even slower. And what if the holes or slots were cut into the tube? How would this affect the ring currents in our model? Well, there would be a weaker magnetic force on the magnet, and therefore the magnet would fall faster than before. All right, thanks.